Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to discuss about the module Energy Loss and Collisions Part 1 from paper Electromagnetic Theory. From this module, students, you may get to know about the following. First, we'll give you an overview of the problem of energy loss by a charged particle in passing through the matter, energy transfer to a free atomic electron by a fast moving charged particle, then the limitation of the formula in the small distance and large distance limits and the corresponding corrections, and results for the case of harmonically bound charge. In this module, we begin our study of collisions between fast moving charged particles. In a collision between charged particles, there is exchange of energy between the particles and there is accompanying deflections. Our aim is to find loss of energy for a charged particle moving through a medium. This is an interesting system for many points of view. Historically, it played an important role in resolving the question of the structure of matter by Rutherford. Energy loss is an important phenomena in particle physics, nuclear engineering, and solid state physics in the study of properties of materials and the radiation damage to the materials. A fast moving charged particle, when it passes through matter, it makes collisions both with the atomic electrons and the nuclei. The resulting energy loss and the deflection of the particle by electrons and the nuclei depend on its mass. If the particle is considerably heavier than electrons, its collision with the electrons and with the nuclei have different consequences. The electron, being lighter than the incident particle, is able to absorb appreciable amount of energy but does not cause much of a deflection of the incident particle. On the other hand, the massive nuclei, it is assumed that the incident particle is much lighter than the nuclei, say a pion, a kaon, a muon, a proton, or an alpha particle, etc., can take up very little energy. But because of very large charge can cause scattering to the incident particle. Thus, loss of energy of the incident particles occurs almost exclusively for collisions with electrons and the deflection of particles from collisions with the nuclei. The scattering is confined by and large to small angles so that the particle keeps a more or less straight path until it loses most of its energy and becomes nearer to the end of its range before it is finally absorbed. If the incident particle is an electron, it loses energy as well as suffers scattering in collisions with atomic electrons. As a result, their path in matter is much less straight. They have rather a short range after which they simply diffuse in the surrounding material. Energy transfer in Coulomb collisions. We now begin by considering the problem of energy transfer to an atomic electron by a fast moving charged particle assumed to be much heavier than electron. Let the mass of the particle be m and charge Ze. If the speed of the particle is large compared to the characteristic speed of the electron in its orbit, the electron can be considered as essentially free as well as at rest. We further assume that the momentum transfer, that is delta p, to the electron is sufficiently small so that the incident particle is essentially undeflected from its straight line path. The recoiling electron also does not move appreciably from its position of equilibrium. Thus, all we need to calculate is the impulse derived to the electron by the electric field of the incident particle. Since the electron is essentially at rest, the effect of magnetic field can be ignored. As we saw in our earlier study of the theory of relativity, the magnetic field produced by a moving charge is of the order of U divided by C square compared to the electric field, where U is the speed of moving particle. Thus, the force due to the magnetic field is of order U into V divided by C square compared to that due to electric field and is negligible even for relativistically moving particle. Now student, here you can see an image where the collision is depicted. So the incident particle has mass m, charge Ze, speed v, and energy is equals to gamma mc square, where gamma is 1 minus beta square raised to power minus half, where beta is v divided by c. For the incident particle, we have used the relativistic formula for energy. The electron, which is positioned at 0, has mass small m and charge minus e. The distance OP is the impact parameter, the distance of closest approach of the particle to the electron. In terms of these parameters, the field produced by incident particle at the position of electron are given by Ex is equals to minus 1 divided by 4 pi epsilon naught into Ze gamma Vt divided by b square plus gamma Vt square whole raised to the power of 3 by 2, and Ey is equals to 1 divided by 4 pi epsilon naught into gamma Zeb divided by b square plus gamma Vt square and whole divided by Ey is equals to 1 divided by 4 pi epsilon naught into gamma Zeb whole divided by b square plus gamma Vt square raised to power 3 by 2, and Bz is equals to 1 divided by 4 pi epsilon naught c into gamma Zeb into beta divided by b square plus gamma Vt square whole raised to power 3 by 2, which is further equals to beta Ey divided by c. Of the x and y components of the electric field, the x component being an odd function of time, its time integral is 0. The momentum impulse is therefore in the transverse direction and has the magnitude delta p equals to integral from minus infinity to plus infinity e into Eyt dt equals to 1 divided by 4 pi epsilon naught into 2Ze square divided by bv. Interestingly, the impulse delta p is independent of gamma. As gamma increases, the peak, which is at t equals to 0, field increases in magnitude, but the duration for which it is significant decrease in inverse proportion, and velocity times the time integral is independent of gamma. The energy transferred to the electron as a function of the impact parameter is then delta W B equals to 1 divided by 4 pi epsilon naught whole square into 2z square e raised to power 4 divided by mv square into b square. The energy loss is directly proportional to the square of the charge of the target particle and inversely proportional to its mass. Thus, for the nucleus of charge Ze, the result would have multiplied by a factor of Z squared divided by 1840A. However, there are Z electrons per nucleus, so that overall energy loss to the nucleus is down by a factor of Z divided by 1840 times A. In other words, it is completely negligible. If, as we have in any case assumed that delta P should be far less than P, then the angular deflection of the incident particle is given by theta, which is equals to delta P by P. Thus, for small deflections, theta is equals to 1 divided by 4 pi epsilon naught into Z e square divided by PVB. This result agrees with the exact expression for the Rutherford scattering of a non-relativistic charged particle for small angles. Therefore, 2 tan theta by 2 is equals to 1 divided by 4 pi epsilon naught into 2ze square divided by PVB. Small distance limit. The energy transfer given by equation 3 has several interesting features. It depends on the charge and the velocity of the incident particle but not on the mass. It varies as inverse square of the impact parameter, so that close collisions involve very large energy transfers. However, as B tends to 0, the formula gives infinite energy transfer, which is obviously meaningless. The formula is actually valid only for large values of B. The energy transfer obviously cannot exceed the maximum possible energy transfer that takes place when the collision is head-on. The maximum energy transfer can be easily calculated from law of conservation of energy and momentum. If a particle of mass m and velocity v hits head-on a particle of mass capital M initially at rest, the amount of energy transferred can be calculated, and it will be delta W maximum equals to 2m gamma square v square divided by 1 plus twice of m by small m into gamma plus m by small m whole square. If the mass of the incident particle is large compared to that of the initially stationary particle, as in case of under consideration, capital M should be much less than m, and the above expression reduces to delta W max equals to 2m gamma square v square. So, equating this value of delta W already obtained, the value of B up to which we can expect our formula to be valid is B minimum equals to 1 divided by 4 pi epsilon naught Z e square divided by gamma mv square. So, we can argue in an alternative way to obtain this limiting value of B minimum. We have assumed that initially stationary electron does not move appreciably during the collision.
the momentum of the electron changes from 0 to delta p, which implies that average speed of the electron is delta p divided by 2m. The time for which the field of the incoming particle is appreciable is delta t, which can be approximated to b divided by gamma v. This implies that distance traveled by the electron during the collision is d equals to delta p divided by 2m into delta t, or d is equals to 1 divided by 4 pi epsilon naught z e square divided by gamma v square is equals to b minimum. Now here we have assumed that capital M should be much less than small m, and we have neglected the denominator in equation number 3. For muons, capital M divided by small m is almost equal to 207, and the denominator must be taken into account if the energy is comparable to or greater than 44 giga electron volt. For protons, it comes to about 340 giga electron volts. For equal mass particles, delta V max equals to gamma minus 1 into mc square. Large distance limit. The result for energy transfer given by equation 3 is approximate for large distances as well. This is because of the binding of the electrons in the atom, which has been neglected since we have assumed the electrons to be free. As long as the collision time is short compared to the orbital period of the electron in its orbit, the collision is sudden and the electrons can be treated as free. On the other hand, if the orbital period is very short compared to the collision time, the electron will make many rounds during the collision. The atom then responds adiabatically, that is, it stretches slowly during the encounter and then returns to the normal when no appreciable transfer of energy is there. So, the dividing line between the two extremes is given by omega delta t b max almost equals to 1, which implies that b max is equals to gamma v divided by omega, where omega is characteristic frequency of the electron. Now students, you can see a figure here, and this figure shows the graph between the impact parameter B and the energy loss delta E as a function of B on the log scale. The dotted curve depicts the approximate form, while the solid curve represents the correct result, taking into account the deviation both at low B and high B. The approximate result is reasonably accurate at intermediate values of B, deviating more and more for low B and high B. The energy loss per unit distance. What we have calculated so far is the energy transferred by the moving particle to a single electron at a fixed impact parameter B. However, as the fast moving particle passes through matter, it sees electrons at various distances from its path. We are interested in the energy loss by the particles per unit distance of its travel. If there are n atoms per unit volume of the matter, and each atom has Z electrons. The number of electrons located at impact parameter between B and B plus dB in a thickness dx of matter is dn equals to nz into B into 2 pi dB dx. Since the energy loss due to the collisions with a single electron is delta EB, the total energy loss per unit distance by the incident particle due to collision with all the particles is dW by dx, which is equals to 2 pi nz into integral delta E B B dB. The integration over B is to be done from 0 to infinity. However, in view of the behavior of delta E as function of B as shown in the figure, we may use the approximate formula and integrate from B minimum to B maximum. In this process, we overestimate the contribution from B minimum to B maximum by a small margin, but ignore a small contribution from outside this range. As a result of this integration, dW by dx equals to 4 pi nz into 1 divided by 4 pi epsilon naught whole square into z square e raised to power 4 divided by nv square into integral from b minimum to b maximum of 1 divided by b square into b db, which is further equals to 4 pi nz into 1 divided by 4 pi epsilon naught whole square into z square e raised to power 4 divided by mv square into ln capital B, where capital B is equals to B maximum divided by B minimum or equals to gamma square mv square divided by ze square omega. The lower limit can be tackled more accurately. A proper treatment of the scattering process for any impact parameter B yields for the energy transfer the expression divided by B square plus B minimum square. Using this expression and integrating up to B maximum yields exactly the same result. The cutoff at B maximum is approximated. Consequently, the expression for B is uncertain to within a small factor. Since it is logarithmic of B that appears in the expression for energy loss, this factor is not of much consequence. The case of harmonically bound charge. We now consider the more realistic case of the electron being harmonically bound rather than being free. This serves as a simple but more realistic model of the energy lost by a charged particle passing through matter. Thus, we have a charged particle of charge Ze, velocity v, and mass capital M, which is much greater than the mass small m of the bound charge of value minus e. As before, we will assume that the incoming particle, being massive, deviates only slightly from its path, which can be taken to the straight line. The impact parameter, the distance of closest approach to the bound charge, is B. The effect of binding is obviously significant only at a large impact parameters. Thus, we can assume that the energy transfer is not very large. As a result, the motion of the bound charge is also non-relatively relativistic throughout, and its amplitude of oscillations about the origin remains small compared to the impact parameter. Under these circumstances, the effect of magnetic part of the Lorentz force can be neglected and only the force due to electric field can be included. Furthermore, the spatial variation of the field over the position of the particle may be neglected and its value may be taken to be that at the origin, the position of equilibrium of charged particle. This is sometimes called the dipole approximation. With these approximations, the equation of motion for the harmonically bound charge may be written as gamma x double dot plus gamma x dot plus omega naught square x equals to minus E by m, E as a function of t. Here E as a function of t is the electric field at the origin due to the moving charged particle. Omega naught is the characteristic frequency of oscillation of the bound charge, and gamma the usual damping factor. Take the Fourier transform of both E as a function of t and x as a function of t. So let x as a function of t equals to 1 divided by under root of 2 pi into integral from minus infinity to infinity x omega e raised to power minus I omega t d omega. And similarly, e as a function of t will be equals to 1 divided by under root of 2 pi into integral from minus infinity to plus infinity e omega into e raised to power minus I omega t d omega. Since xt and also et are real, so on taking the complex conjugate, we can obtain x as a function of t equals to x conjugate as a function of t equals to 1 divided by under root of 2 pi into integral from minus infinity to plus infinity of x conjugate omega into e raised to power I omega t d omega equals to 1 divided by under root of 2 pi into integral from minus infinity to plus infinity x as a function of minus omega into e raised to power I omega t d omega, which implies x minus omega is equals to x conjugate of omega. Similarly, e minus omega is equals to e conjugate of omega. On substituting into the equation of motion, we obtain x omega equals to minus E by m into E omega divided by omega naught square minus iota omega gamma minus omega square. Similarly, E omega equals to 1 divided by 2 pi into integral from minus infinity to plus infinity e as a function of t into e raised to power I omega t dt. Thus, et is dependent on e omega, which is dependent on x omega and xt. However, what we are really interested in is the energy transferred to the bound charge in the collision rather than its detailed motion. Thus, energy transfer can be found by considering the work done by the incident particle on the bound one. So, the rate of doing work is given by dw by dt equals to F into dx by dt, which is equals to minus of E into EV. The total work done by the particle passing by on the bound charge is thus delta W, which is equals to integral minus infinity to infinity dw by dt into dt, which is equals to minus of E into integral minus infinity to plus infinity of v dot E dt. In the dipole approximation that we have made, Et is the electric field of the incident particle at the position of equilibrium of the bound charge. Thus, we can get delta W equals to minus E into integral minus infinity to plus infinity dt into 1 divided by under root of 2 pi into integral minus infinity to plus infinity of minus iota omega into x omega into e raised to power minus I omega t d omega into 1 divided by under root of 2 pi integral minus infinity to plus infinity into e dependent on omega dash into e raised to power minus iota omega dash t d omega dash, which is again equals to minus e into integral from minus infinity to infinity and again integral minus infinity to plus infinity of minus I omega x omega e omega dash d omega into d omega dash into 1 divided by 2 pi into integral minus infinity to plus infinity e raised to power minus iota omega plus omega dash t dt. Now we use the Fourier representation of the delta function, that is delta x equals to 1 divided by 2 pi integral minus infinity to plus infinity e raised to power minus iota xt dt. Finally, on using the expression for x omega in terms of e omega, we obtain delta W equals to minus of 2 e into real part of integral 0 to infinity of iota omega e by m into mod of e omega square divided by omega naught square minus I omega gamma minus omega square into d omega. On rationalizing the denominator in the integrand, we obtain delta W equals to e square by m into line integral from 0 to infinity of 2 omega square gamma into mod of e omega square divided by omega naught square minus omega square whole square plus omega square gamma square into d omega. We continue to make further approximations to get an idea of the effect of binding on energy transfer. For small gamma, the integrand peaks sharply around omega equals to omega naught in an approximately Lorentzian line shape. The Lorentzian function is the singly peak function, which is given by Lx equals to 1 divided by pi into gamma by 2 divided by x minus x naught whole square plus gamma by 2 whole square, where x naught is the center and gamma is a parameter specifying the width. The Lorentz function is defined so that integral from minus infinity to plus infinity of Lx dx is equals to 1. Since the integrand is sharply peaked around omega equals to omega naught, we can replace the electric field E omega by E omega naught and its value at the maximum of the sharp peak. So we will get delta W equals to 2 E square by m into mod of E omega naught square into integral from 0 to infinity into omega square gamma divided by omega naught square minus omega square whole square plus omega square gamma square into d omega. So, by changing the value of omega by gamma equals to x, the integral becomes integral 0 to infinity of x square dx divided by omega naught square divided by gamma square minus x square whole square plus x square. This integral has the value pi by 2 dependent of omega naught by gamma. Thus, finally, we have delta W equals to pi E square by m into mod of E omega naught whole square. This is a very general result for energy transfer of a non-relativistic oscillator by an external field. In the present case, the field is produced by a moving charged particle. For a particle with charge Ze, velocity v, and impact parameter b, the non-zero electromagnetic field at the origin O is given by equation 1. Thus, E omega naught is given by the inverse Fourier transform. So we'll have E omega is equals to 1 divided by under root of 2 pi into integral minus infinity to plus infinity of et e raised to pi I omega t dt, and using equation 1 for the y components of electric field, we obtain Ey omega equals to 1 divided by 4 pi epsilon naught into Ze gamma b divided by under root of 2 pi into integral minus infinity to infinity into e raised to pi I omega t divided by b square plus gamma square v square t square whole raised to power 3 by 2 dt. Now, on changing the integration variable to u equals to gamma vt by b, we get e y omega equals to 1 divided by 4 pi epsilon naught into Ze divided by under root of 2 pi b v into integral from minus infinity to infinity into e raised to power I omega b u divided by gamma v divided by 1 plus u square raised to power 3 by 2 du. The integral in this equation is related to the modified Bessel function k1. We have the integral representation of modified Bessel function kvz given by kvz equals to 2 raised to power v gamma v plus half divided by under root of pi into z raised to power v whole into integral 0 to infinity of cos zt divided by 1 plus v square raised to power v plus half into dt. In particular, K1z equals to 2 gamma 3 by 2 divided by root pi z into integral 0 to infinity cos zt divided by 1 plus t square raised to pi 3 by 2 dt equals to 1 divided by 2 pi integral from minus infinity to infinity cos zt dt divided by 1 plus t square raised to pi 3 by 2, which is equals to 1 divided by 2 pi integral from minus infinity to infinity e raised to pi I z t dt divided by 1 plus t square raised to power 3 by 2. Similarly, on partial integration, we can get k naught z equals to 1 divided by 2I z into integral from minus infinity to infinity t into e raised to power I z t dt divided by 1 plus t square raised to power 3 by 2. So, we can get e by omega is equals to 2 by pi raised to power half into 1 divided by 4 pi epsilon naught ze by bv into omega b by gamma v into k1 of omega b by gamma v, where k1 is the modified Bessel function of order 1. We do the calculation for the x component in the similar fashion. Similarly, we get Ex omega equals to minus of 1 divided by 4 pi epsilon naught Ze gamma v divided by under root of 2 pi into integral minus infinity to plus infinity t e raised to power I omega t divided by b square plus v square gamma square t square raised to power 3 by 2 dt. The same change of variable u is equals to gamma vt by b, and the integral yields e x omega equals to minus of iota 2 by pi raised to pi half into 1 divided by 4 pi omega naught. Ex omega is equals to minus of I into 2 by pi raised to pi half into 1 divided by 4 pi epsilon naught into Ze by b gamma v into omega b by gamma v into k naught omega b by gamma v. The energy transfer to a harmonically bound charge can now be calculated explicitly. Hence, delta Wb equals to 1 divided by 4 pi epsilon naught whole square into 2z square e raised to power 4 divided by mv square into 1 by b square into xi square k1 square of xi plus 1 divided by gamma square into xi square k naught square xi, where xi is equals to omega naught b by gamma v or equals to b by b maximum. The factor outside the square bracket is just the approximate result for energy loss. The asymptotic forms of k0 and k1 for large and small arguments are well known, and for xi tending to 0 will get xi k0 xi tends to 0 and xi k1 xi tends to 1. For xi tends to infinity, we'll get kv xi tends to under root of pi by 2 xi into e raised to pi minus xi, independent of v. Using these asymptotic forms, we see that the terms in the square bracket tends to 1 for xi less than 1 and 2 1 plus 1 divided by gamma square into pi by 2 xi e raised to power minus 2 xi for xi much greater than 1. Since we see that the energy transfer is essentially the approximate result of equation 2 for b much less than b maximum and for b much greater than b maximum, it falls off exponentially to zero. This was an expected result from the qualitative argument given earlier. So students, let us summarize what we have learned in this module. An overview of the problem of energy loss by a charged particle in passing through matter has been given. Formula for energy transferred to a free atomic electron by a fast moving charged particle has been derived. Limitation of the formula in the small distance and large distance limits and the corresponding corrections have been given. Energy loss by moving particle per unit distance has been obtained, and the effect of the binding of the electron on the energy transfer has been discussed, and the formula for harmonically bound charge has been derived. Thank you.